Hello class. Today we're going to finish up our physics unit. We're going to do a couple quick examples on mechanical energy, and then we're going to look at graphing mechanical energy. So let's do a quick example here. If a ball is sitting on a vertical spring and is pushed down 4 centimeters with a force of 10 newtons, we want to calculate the speed when the ball leaves the spring. Now, if I was to draw this, that would be our ball, and we have a spring that is being compressed. Now really, the only important thing here is that you have some sort of distance and a force that's been applied. So we have force of 10 newtons and a distance of 0.04 meters. Now hopefully you'll notice that there's a relationship between force and distance. Even though we're being asked to calculate the speed, there's still a relationship with force and distance. So that relationship is work. Work is equal to force times distance, which is going to give us 10 times 0.04, which is 0.4 joules of work. Now why do we care about that? Well, you might recall that work is equal to the change in energy. So at the beginning you had nothing, but then you added work by pushing down on the spring. That's going to give us a change in energy. So that change in energy is 0.4 joules. When you release the spring, you now have kinetic energy. It's being transformed from potential energy when you squish the spring to kinetic energy. And you know that the total energy has to add up to this much work. So we can use that number as our total energy. And remember, we're using kinetic energy, so that's 1/2 times the mass times speed squared. We don't have mass. I should give you mass. I'm going to say the mass is equal to 0.3 kilograms. So if we wanted to solve for V, we're going to multiply both sides by 2. So 2 times 0.4 is equal to our mass of 0.3 times V squared. You can divide both sides by that 0.3. You get V is equal to the square root of 2 times 0.4 divided by 0.3, which is equal to 0.8 divided by 0.3 square rooted. So you get 1.663 meters per second. Our question has one significant digit, so it would be 2 meters per second. Okay, so that's kind of a spring one that's similar to the one that's in your assignment, number 2. This hopefully might help you with some of the work that you have to go through to get there. The big thing is that force times distance is that work formula, and work is related to energy by being the change in energy. Alright, so for our last numerical example, I'd like to try a physics 20 example. So we have this ball that's sitting on an inclined plane. It's being held there and then is let go. Obviously this ball is going to roll down the hill, and it's going to pick up speed as it rolls. We can use energy to find out how fast it's going. Even though it's going to go down a hill rather than being in a free fall, the same principles of energy apply. Energy is conserved. So all we have to do is find the mechanical energy at the beginning and equal it to the mechanical energy at the end. At the beginning, we have our mass of 1 kilogram. We know our height is 0.5 meters above the ground. That's this height here. Or I guess it's actually from the bottom down to here is 0.5. And we know it's being held, so our velocity initial is 0 meters per second. When it's released, down here, we still have that same mass of 1 kilogram, but this time our height is equal to 0, and we're going to have some speed. That's what we don't know. So this is at point 1, and this is at point 2. So let's do this. Let's do EM1 must equal EM2. And let's solve it. We have EP1 plus EK1 must equal EP2 plus EK2. We know that EK1 is 0 because there's no velocity. And we know that EP2 is 0 because there's no height. So you're left with EP1 equals EK2, or mgh1 equals 1/2 mass times velocity squared. Now let's isolate for v squared, or v by itself. We can divide both sides by m, and both m's cancel out. So you're left with gh1 equals 1/2 v squared. Now you can multiply both sides by 2, and you get 2gh1 is equal to v squared, or you can say the square root of 2gh is equal to v, which tells us our v2 is equal to the square root of 2 times 9.81 times that height of 0.5 meters. Plug that into your calculator, you're going to get 9.81 times 2 times 0.5 is, well, just 9.81, and the square root of 9.81 is 3.13 meters per second. And our significant digits call for 2 in the final answer, so V2 equals 3.1 meters per second. And that would be your final answer. So Physics 20 is just a little bit of an extension on what we're learning now. Hopefully this helps, and when you see this question next year, you can send me an email and tell me that you understand it, hopefully. Okay, for the last concept, we're going to talk about mechanical energy as a graph. Now, in a graph of the energy associated with a pendulum, we know a pendulum has this type of motion. It's going to start somewhere above its original height, and then it's going to rock back and forth, back and forth, back and forth. So what we're going to do is we're going to graph at a few different points. We're going to graph it here, we're going to graph it here, and we're going to graph it at the top up here. So I'm going to write that down as our first place, our second location, and our third location. Now I wanted to have 3 different types of energy. We know we have EK, EP, and mechanical energy. So I'm going to make different colors for each one. For mechanical energy, I'm going to make it red. For potential energy, I'm going to make it green. That's gravitational potential. And for kinetic energy, I'm going to make it pink. Now the mechanical energy, or let's start with potential energy. At position 1, we have the maximum amount of potential energy. It's all gravitational potential at that point before you let go. Then when you let go, at position 2, you end up with 0 potential energy. This is an energy. You have 0 potential energy. But then back at point 3, you have that same amount of potential energy that you had at the beginning. And what that looks like is this. Something like that. Now let's look at kinetic energy. At the beginning, right before you let go, you have 0 speed, meaning you have 0 kinetic energy. But at point 2, you have a maximum amount of kinetic energy. But how much energy do you have? Well, you're going to have the same amount that you had as potential energy at the beginning, because energy can't be destroyed. This whole entire energy here has to equal the whole entire energy here, which means that this kinetic energy where potential energy is 0 must equal the total amount of energy. And then again at point 3 it stops for a second, so it goes back to 0. So it looks like the exact opposite for kinetic energy. What about mechanical though? Mechanical energy here, EM1, EM2, and EM3. You might remember from last lesson that the mechanical energy in the system doesn't change. It just doesn't change, it's conserved. So at the beginning, your mechanical energy is equal to the total amount of energy from kinetic and potential sources. And it doesn't change throughout the whole experiment. It stays the same. So mechanical energy here is just a straight line. Kinetic energy, oh that's potential, sorry, is a curve like a happy face, and then kinetic energy is a curve like a frown. But the big takeaway here for you is that mechanical energy looks like that. Now let's try one more, but with an object falling. So if I drew my object here and the ground, this is our total energy. We're going to look at here, we're going to look at here, and we're going to look at it right before it hits the ground. We'll start 1, 2, and 3. For gravitational potential energy, EP. Obviously at point 1 we have a lot of potential energy. In fact, all the energy is potential energy at that point because we have this big height here. So it's going to start up here as the maximum amount of energy. At point 2, about halfway through, then you have half that amount of energy. And at point 3, when it's right above the ground, your height is 0, your potential energy is 0. And you're left with this straight line for your potential energy. Looking at kinetic energy, at the beginning, right before it's dropped, you have 0 energy, 0 joules. At this point, point 2, you have exactly the amount of energy that you had as potential energy, because those two added up have to equal your total mechanical energy that you started with. And then at point 3, that's when you have your highest amount of energy. And that total amount of energy has to equal the total amount of energy you had in the system at the beginning. So you get this nice straight line going upwards. But again, just like in this last case, your mechanical energy is equal to the total amount of energy at the beginning. So this value plus this value of 0 gives us this total amount here. And then in the middle, it's this total from kinetic and potential added up together, which makes your total mechanical energy, right here, because it's both potential and kinetic added, be this much times 2. And then in the end, that whole mechanical energy is made up of kinetic energy. So once again, look at your mechanical energy graph. It is supposed to be a straight line. There we go. It is a straight line. EM stays the same throughout. And at every single point in it, it's made up of the amount of potential energy plus the amount of kinetic energy to give you this total amount throughout the entire system. So that's all for physics that we have. For the rest of our time in physics, I would like you to finish your practice questions, finish both physics assignments, and study for your test that's coming up. Have a great day.